So we will begin. So we said we can do UV-Vis or absorption type spectroscopy in a complex mixture because those absorbances are going to be additive. So if you had red dye and blue dye together, you would end up absorbing both sets of wavelengths. There would be some overlap, and we can, in that overlap region, just add up the absorbances of each component to give us the total absorbance. So the absorbance from at a particular wavelength from component 1 plus the absorbance of component 2 at that wavelength, add them all up, that's going to give you your overall absorbance. We can usually break that down further by saying that it's going to be related to the absorptivity of component 1 at that wavelength, the path length times the concentration of component 1. And then plus the absorptivity of component 2 plus the path times the path length times the concentration of component 2 at that wavelength. So how does that actually play out in reality? Well, here is an example where we've got an analysis of a mixture. So we've got a cobalt and nickel complexing with quinoxyl aniline dithiol. We have a 250 milligram soil sample. It's dissolved, you develop color with a complexing agent, and then you dilute that to 100 milliliters. Calculate the percent of cobalt and nickel in the soil. So we're looking at two different elements. They're still going to be treated the same way, but they're going to form complexes that have different colors. And if we measure at two different wavelengths, we can figure out what the concentration is of each of those components, even though at each of those individual wavelengths, the absolute absorption is going to be the sum of the absorption of each component. We don't necessarily know what it is. So we're given some data that says at 510 nanometers, the absorbance of the cobalt is 3.64 times 10 to the fourth, and the absorptivity of the nickel is 5.5 times 10 to the third. And then at a second wavelength, 656 nanometers, the absorptivity of the cobalt is 1.24 times 10 to the third, and the absorptivity of the nickel is 1.75 times 10 to the fourth. And so your cobalt complex absorbs more 510 light and a little bit less 656. So this is going to look a little redder, and your nickel complex absorbs less in this 510 greenish area, a little bit more red, so it's going to look a little more greenish. So we then do an experiment. We measure the wavelength at 510 nanometers. We measure the wavelength at 656 nanometers. How can we then pull this into something where we get the concentration of cobalt and we get the concentration of nickel in our original sample? And the answer is math. Right? So we've got two unknowns. This means we're going to need two equations in order to do this. And so all we're going to do is we're going to set up a system of simultaneous equations where we've got the absorptivity or the absorbance at 510 and the absorbance at 656. And we see the absorbance at 510 is equal to, right, our absorbance of the cobalt and our absorbance of the nickel. And we've expanded that to say that we're looking at the absorptivity times the cobalt concentration plus the absorptivity of the nickel times the nickel concentration is equal to 5.17. And then at 656, the total absorptivity over here, 0.405, is equal to the absorptivity of the cobalt times the concentration of cobalt plus the absorptivity of the nickel times the concentration of the nickel. And so we've got two unknowns, concentration of cobalt and the concentration of nickel. We've got two equations. This is now solved. So we're going to solve for nickel, the concentration of nickel in the first equation. So we'll take this first guy and we'll rearrange it to solve for nickel. So we'll get 5.17 minus 3.64 times 10 to the fourth times the concentration of cobalt over 5.52 times 10 to the third. Now, when I was doing this, this was confusing AF because I don't have a math brain. And people who have math brains are looking at that going, oh, yeah, it's just for simultaneous equations, and you just do the things, and you can do it by substitution or a matrix or what have you. No, my brain did not work that way. I I had to literally go through and put this as like, this guy is X and this guy is Y, and then I could solve it. Why? I don't know why. It's just how my brain works. If I put in the concentration of cobalt, my brain went, I can't do that. That's not accessible to my math skills. But if I made that X and Y, then I could. Can you go ahead and throw this into a simultaneous equation solver, either on your calculator or online? Yeah, do that. Go ahead and do that on a homework or a lab or something like that. This would make a very, very good test question. It just takes a really long time. So whether or not this shows up, I don't know. So, but definitely pay attention on how to at least in theory do this. So what we're doing is we're taking this first equation, rearranging it in terms of this variable. So we end up with this newly rearranged equation where our concentration of nickel is on the left. This is going to allow us to do substitution. We're going to take this equation here where it says concentration of nickel and the concentration of nickel over here. We're just going to take this whole thing and plug it into there. And so now we get 1.24 times 10 to the third times the concentration of cobalt plus 1.75 times 10 to the fourth times, and this is where our concentration of nickel was, 5.517 minus 0.364 times 10 to the fourth times the concentration of cobalt over 5.52 times 10 to the third is equal to 0.405. And so we've taken our first equation, rearranged it, plugged it into our second equation. Now we've got one equation with one unknown. And then it's just a matter of going through and expanding that and simplifying and solving for cobalt. So we get 1.24 times 10 to the third times the concentration of cobalt plus 1.64 minus 1.15 times 10 to the fifth times the concentration of cobalt is equal to 0.405. Move that on over. Divide. We end up with a concentration of cobalt is 0.405 minus 1.64 divided by negative 1.14 times 10 to the fifth, and that's going to be equal to 1.08 times 10 to the minus 5 molar. Once we've got this, we're just going to go back to that rearranged equation where we solve for the concentration of nickel, and now we're going to take our concentration of cobalt and we'll plug that in right here. So we'll end up with 5.17 minus 3.64 times 10 to the fourth times our concentration of cobalt, which we just found, divided by 5.5 times 10 to the third, which is equal to 2.24 times 10 to the minus 5 molar. And we're basically done, right? Once the trick here is realizing that if I'm looking, if I'm looking for two variables, concentration of cobalt and the concentration of nickel, I need two equations. My two equations are going to be the sum of the absorbances at two different wavelengths. Right? Found the amount of cobalt in the soil. They wanted that as a percentage, so we're going to take our millimoles per liter, our concentration in moles per liter. I'm then going to multiply that by our volume, and we're going to end up with 0.063 milligrams. And we'll divide the milligrams of cobalt by the milligrams of our total soil sample, multiply by 100, and we get 0.025% cobalt. And we can do the same thing for the nickel, where we take its concentration in millimoles per milliliter. Right? The reason why we want to do millimoles per milliliter is that when we use the molar mass, it gives us right into milligrams times our volume, and we're going to end up with 0.131 milligrams of nickel. Take our 0.131 milligrams of nickel, divide by the total mass, times 100, gives us 0.053% nickel. Okay. So that was the hard part. Let's talk about what happens when matter when light comes out the other side. And so that was the last and most complicated thing we'll do with absorbance spectra. Okay? What happens when the light matter interaction goes the other way and our matter is emitting light? Well, that gives us something called an emission spectrum. And they come in a couple of different varieties or flavors. And they're usually determined by how the number of wavelengths that you get and how wide a peak would be. So you can have a line spectrum, a band spectrum, or a continuum, or a black body emission. So a line spectrum would be something like the sodium line emission, or here's mercury, where you've got this atomic emission process. The energy levels are very well defined, very discrete. You're going to end up with a very narrow range of wavelengths, plus or minus maybe like a quarter of a nanometer. It's not a very broad range. And then you've got a band emission. So if you're looking at something like green fluorescent protein, it's going to be green, and it's going to occupy, you know, maybe 500 nanometers plus or minus 20 nanometers. So when they talk about a band, they're talking about a range of values. And green fluorescent protein is now available in different colors. So you can get like a red fluorescent protein that'll maybe emit light between 800 and 650 nanometers. Right? So it's a pretty broad band. It's a pretty wide range of frequencies or wavelengths that are available. A continuum is giving you photons in every wavelength. And that's called a black, and that's usually coming from something called a black body radiator. So as things get hot, they're going to give off photons in a predictable way over every single wavelength available. Right. So if you got two different emission spectra, right, hydrogen versus helium, those lines in hydrogen are coming from the n equals 6 to n equals 2, n equals 6 to n equals 5 to 2, 4 to 2, and 3 to 2 transitions. It's pretty simple for us to predict and model that in hydrogen. The Rydberg equation, which you may remember from Chem 120, is going to be able to describe this for you. It gets a lot more complicated as soon as you get in an extra electron and an extra proton and go to helium. Right, so helium starts getting more complex, and by the time you get into other things, it can get even more complex, and so you're going to start to see lots and lots of lines. Black body radiation is something that all things do. So as temperature increases, materials will emit energy in the form of a photon. The hotter the material, the more energy it has, and the bluer the peak of the Planck curve. The shape of this curve is going to follow a Boltzmann distribution. And so how does the intensity of the electromagnetic radiation emitted by a black body, so perfect absorber, that's why it's called a black body. So it's going to be a perfect absorber for a cavity radiator. So the reason why they called it cavity radiator is they were doing experiments where they were taking literally a furnace, and they'd have a little hole in the furnace, and they would look into this cavity or the hole in the furnace. How does it depend on the frequency of radiation or the color of light? And the temperature of the body. So as you increase the temperature of something, you're increasing its molecular motion, but you're also going to increase excuse me, the amount, and you're going to shift the emission peak of the photons that it gives out. And it's going to follow this basic trend. And so people have made this measurement and observation back in the 1800s, where it's like, okay, if I get this thing hotter, right, it's going to glow kind of red hot, and then it's going to go yellow hot, and then it's going to look white hot, because you're starting to get all kinds of photons in from a range of wavelengths that you can see. And they had plots like this, and the problem was that classical theory, if you are treating light as a wave and not as a discrete packet of energy, at 5,000 Kelvin, your emission should go exponential. And this is what's called the ultraviolet crisis in physics, is that classical theory predicts you're going to get infinite amount of energy out. And obviously you don't get infinite amount of energy out. You get a finite amount of energy out, and it comes back down over here. And that's where Planck comes in. And Planck's research and his thesis was on quantizing energy and kind of correcting for this ultraviolet catastrophe where classical theory was not matching up at all with what was happening. And at the time, he was like, yeah, kind of fits. Like, you know, if you do this, then like it matches the data a little bit better. And kind of by accident, he introduces the whole idea of quantized light or photons and kind of kicks off the whole study of quantum mechanics. So, but for us, if you get something hot, it gives off light. As you get hotter and hotter, it gives off more light, and where this peak shifts is going to depend on how hot it is, the total amount of energy radiated per unit area, per unit time, J squared in watts per square meter by a black body is related to its temperature in kelvins and to the Stefan-Boltzmann constant by this little equation here, where it's J star is equal to sigma to the fourth power. And you're going to see some stuff to the fourth power a lot if you get into more of these light studies. But if you also talk about what is the temperature of a light bulb, right? So sometimes you'll see a temperature rating on a light bulb, and that's what this is doing here. Here is your temperature in Kelvin, and it is predicting basically this on top of a color space for you. So if you want a hotter light, then it's going to be giving you more blue light. It's going to look a little bit whiter to us, whereas something that is a cooler light is going to look a little bit more red or orange. Right, so luminescence is another kind of way that light can be emitted from matter. So luminescence is not going to rely on thermal radiation necessarily. Oftentimes it's going to rely on an incoming photon being absorbed and then having that energy re-emitted as another photon. And so here we've got our Jablonski diagram where we're starting off at a ground state. You have some incident radiation that gets absorbed into one of two excited states. That energy can be released as a photon going from 2 to 1, or it can be released as a photon going from 2 all the way back down to 0, or it can be released as a photon going from 1 back down to 0. We can also have some movement or loss of energy in a non-radiative pathway. So these dashed lines represent an energy loss that is not coming off as a photon. So if we're looking at a regular old molecular absorption, this is the process we've seen for UV-Vis absorption. We're going from a ground state up into some excited state, maybe a ground state into an excited state, plus a little bit of vibrational energy. Right? We can have some vibrational relaxation in those molecules that will bring them back down to the ground vibrational state of a different electronic state. And so you excite a molecule, it's got a little bit more than just the energy to go to a new electronic state. So you've changed its electron configuration, now its electrons are moving, and you've imparted a little bit more molecular vibration to it. Well, that molecular vibration is pretty easy to lose, right? It just bonks into another molecule, and now that other molecule has the energy and it vibrates. So you can have this vibrational relaxation happening. You can also have a relaxation that happens between an electronic state and another electronic state. So you're going to go from the ground vibrational state of a higher electronic state down to the highest vibrational state of a lower electronic state. Right? And that's a process called internal conversion, where you're converting from one energy state, one electronic state to another electronic state. You then can dump or give off that energy in the form of a fluorescence photon down to a lower electronic state, but a variety of vibrational states. And so our fluorescence process is light comes in, right, gets absorbed. We bring it down to a ground vibrational state of an electronic state, right? Or we have to undergo some sort of internal conversion, and then that light gets emitted again to a lower electronic state, but a variety of different vibrational states. And it's these variety of different vibrational states that are going to show up as little peaks inside our fluorescence spectrum. And so that's where the light is going from. Right? Now we're going to talk about instrumentation. So instrumentation is going to follow one of two basic plans, depending on if you are on the emission or the absorption side of the sample. They're all going to share some similar components. They're all going to have a sample, right? You got to have some matter to look at. You're going to have some source of photons, right? So if you're doing a UV-Vis experiment, right, it's that little light bulb in there, right? If you're doing a fluorescence experiment or an emission experiment, maybe your sample is the source. You're going to have some sort of wavelength analyzer, so something to select or disperse the light. That's because you only usually want to look at one wavelength at a time, right? Our lambda max, if we're doing our UV vis absorption, or what is our emission line if we were doing that iron for the ICP. Then you're gonna have some way to measure it, some sort of detector or meter. And I can't draw any on the board, so I've got some as slides. So this is their basic, what we call a block diagram. This is different from a schematic or a detailed drawing. This is just showing the different components as little blocks. Right? Absorbance is measured by using an instrument called an absorption spectrophotometer, where we've got a light source. And the first component of an absorption spectrophotometer is a light source, which is a lamp that produces many different wavelengths. All right, so excuse me, the light source produces light of many wavelengths, and then the monochromator is going to break light into its component colors or wavelengths, and we're going to block everything except for one color. Right, so light will come in, we'll get a little rainbow out, and we're going to pick off just one wavelength at a time for a monochromator. There are instruments that rely on what are known as polychromators. So rather than just picking off one wavelength at a time, you are looking at all of your wavelengths at a given moment in time. You are still going to need something to spread that light out there. Then you've got next is the sample. And that's where your blank or your cuvette is placed if you're doing absorbance spectroscopy. As that now monochromatic light would transit your sample, some of it's going to be absorbed. We would measure our number of photons in versus our number of photons out. Right? So if you've got a really simple one, you take your sample out, you measure what the power is at your detector, then you put your sample in and you measure the new power. Right? And then next, where you measure it is going to be some sort of light detector. It's going to measure the irradiance of the monochromatic light that is transmitted through the sample. Right? So some of the common cuvettes or sample holders, we're going to go from the beginning towards the end. For visible in UV vis spectroscopy, liquid sample is usually contained in a cell called a cuvette. The good ones are going to have flat fused silica SiO2 quartz faces. Glass provides a cheaper alternative that is suitable for visible spectroscopy, but not for UV vis spectroscopy because glass absorbs in ultraviolet. Nowadays, we've got plastic cells as well. So we'll see a little chart that has some of those in a second. The reason why plastic cells are becoming more common is because they're cheap, right? We will see the cost of some of these things in a second. They're going to come in different form factors. Probably the most standard is this guy right here, which is the 1 centimeter path length. So that the width from one side to the other is 1 centimeter. You can get ones that are in different volumes or in different shapes that still maintain that 1 centimeter path. So here is one that is a microcell over here. It's got a reduced volume, but the path length as you go from this side to this face is still going to be 1 centimeter. You can have ones that are very narrow, like this guy's a 1 millimeter path. So if you're working with a very optically dense or concentrated solution, maybe 1 centimeter is going to absorb way too much light. Maybe you only need 1 millimeter. If you are working in a situation where you might need to do some online sampling processes, or if you want to hook it up to a chromatograph, you can use a cylindrical cell like this, or a flow cell like this. Oftentimes these guys, these cylindrical cells, they're pretty long, and there's something that you might see if you were trying to measure the absorbance of a gas. So in PChem, we may or may not get to do a FTIR experiment where we measure the infrared absorbance of a gas. So doing gas phase sampling is a little tricky, so you don't see that often, but that's what one of these guys looks like. A flow cell lets liquid flow in and out of it. A thermal cell is one that's going to have a little thermal jacket around a flow cell. That's going to help keep the temperature stable. So the materials for our renewable cuvettes are either going to be glass or they're going to be quartz fused silica. The wavelength range for glass is going to be from the infrared all the way up to about 340. And then you're going to start to see absorbance from the glass itself. The advantage of a glass cuvette is that it costs maybe, probably about $50 for a glass cuvette, whereas a pair of matched fused silica quartz cuvettes can be like $150 to $300, depending on what they're made out of and whether or not they're a fluorescence cuvette or whether they're a UV-Vis cuvette. So most of the time, like you guys saw, we're going to use a disposable cuvette because they cost somewhere in the range of 10 cents to $1, right? And then when you're done, you can throw them away. So with these guys, if one of them, and that happened one time, I was doing a lab, poor Murray. So he's sitting there and he's got one of my pair of like $300 cuvettes. And I'm like, be careful with those. And he's like, okay. And I turn my head and I hear tinkle and I'm like, oh no. And I look over and he's like, you dropped it, didn't you? And he's like, yeah. I'm like, it's okay. So yeah, and I'm like, oh, no, I have an unmatched. It's just sad. But most of the time we're going to work with plastic ones because they're cheap, they're disposable. They are not going to go out into the UV as far. Sometimes you can get ones that go into the near UV, right? That are going to go out a little bit further than this glass would, like the cyclic olefin copolymer guy and the methacrylate. They're going to go out a little bit further than the glass ones would. But the disadvantage of those is that if you are working with something that's an organic solvent, and plastic often does not play well with organic solvents. So if you put acetone into your polystyrene cuvette, you're pretty soon going to have a goopy mess on your hands and not a measurement. Right? So the letters Q or UV indicate that a cuvette has few silicon windows and that it is suitable for both UV and visible spectroscopy. If you are working for something that is at a longer wavelength, oftentimes those are made out of a little bit more exotic materials. So you will have a window that is made out of sodium chloride. So you will have these things that are called salt plates or salt lenses, and they are literally made out of either sodium chloride or potassium bromide. And some of them might be 2,2 ionic compound where it's a zinc selenide. Trying to remember what the ones are on the little ATR ones that we've got. I think those are diamond rather than zinc selenide. But the windows can be made out of diamond as well. Obviously, that's going to be expensive. The liquid samples that are prepared in solvents such as carbon disulfide or carbon tetrachloride or dichloromethane. Right? So a lot of these organic solvents are things that you want to get IR spectra of. You can't put them into plastic, right? So you're going to need to use this material that's going to be transparent in that region. So something that's a salt, and then something that is not going to dissolve in your organic solvents. Water and alcohols absorb in the infrared, and they're not going to work with a lot of cell materials. Solid samples. So when you're doing sampling for IR, one of the ways you can make do your sample prep for IR is you take a mineral oil. So you basically take a mineral oil and you powder stuff up and you grind it up and you smear this thing on as a thick paste, which is a dispersion called a mull. And Nujol oil is a commercial product that kind of ended up finding its way by accident into a very niche market. So Nujol mineral oil was originally sold as a laxative and purgative. So back in the end of the 19th century and the beginning of the 20th century, regularity was a real big health issue. And so products that made you poop were a large sector of the healthcare market. And so Nujol was one of those things that was pretty commonly available. And so people who were doing IR spectroscopy were like, yep, it's not going to dissolve my salt plate. I can make a nice spready mixture of this stuff and take my powder that I'm looking at and put this onto a salt plate and not have it dissolve. And then you sandwich this guy in between some potassium bromide plates. And then you get your spectrum. And you wash it off with some chloroform. So the story time, kids. So one of the things that you now have available to you is a ready availability of what's called an FT or Fourier transform infrared spectrometer. You can do regular old infrared spectroscopy using what's called continuous wave spectroscopy, in which the instrument is set up exactly like one of our UV vis instruments, where we've got a light source, we've got a wavelength analyzer that's going to be a monochromator, our sample, and our detector, and you move your wavelength analyzer, and you can basically set it up just like any other conventional optical spectrometer. So when I was doing this, you would do this kind of like, you get a little salt base, they're not that big, and you'd take your new gel ball and you'd smear it on there, you'd smear your sample on there, and you'd mount it vertically for reasons that I do not understand. You mount the sky vertically, and then the infrared light would come through, and then you would clean it, and usually you would clean it with a squirt bottle full of chloroform, because chloroform is a good organic solvent. And so, being a dumbass, I was like, hey, I wonder if chloroform works like it does in the movies. So I take a chem wipe and I spread some chloroform on it, and I'm like, oh, and I start to go down. And it was, one, a really dumb thing to do, and two, it's why we work with lab partners, because my lab partners saw me being a dumbass, ran over and caught me before I fell onto the ground. So chloroform works pretty much as advertised in the movies. So it's not like the Hollywood clip. Yeah, don't do that. Learn from my mistake, kids. Don't do that. Alternatively, you can prepare a sample for IR by taking some potassium bromide and then squooshing it down into a pellet. As you squoosh your KBR and your whatever it is you're looking at, your analyte, and you smush these guys together, you end up with glassifying your potassium bromide. You basically make a pellet that's KBR glass. That KBR glass is invisible to the infrared light that's coming through. Your Nugel mol, you end up with spikes in there because of the Nugel, but you just subtract those out mathematically. You can use the moles and KBR for qualitative purposes only, and that's because, not because of anything wrong with Beer's law. You can still do Beer's law in the infrared. It's just that, how thick did you get that mole? How evenly is it distributed? If you've got a pellet, like, how sure are you of that pellet thickness? So you can't really reliably say that your concentration is even throughout that, and that you know exactly what your path length is. So that's why you don't see as much quantitative IR work. Right, so you can have transmission differences between cuvettes. So an empty glass cuvette reflects about 13% of your visible incoming light. So if you ever try to take a flash with through a window, you're seeing that light bounce off. To compensate for the differences between that, you're going to do baseline absorption. You also have positioning error with your cuvettes, right? So whether or not this cuvette is dead on or whether it's tilted slightly off to the side is going to affect both the path length, so the light, the distance the light travels through, as well as that reflection process. So positioning error, you would think, would not be a big one, but this 13%, if you're changing that and changing that angle by just a couple of degrees, you can introduce upwards of a 5%, almost up to a 10% error in your observed absorbance because of a positioning error. Other things that you got to do too is you got to make sure that you don't have dirty fingerprints all over this, right? So you're going to wipe that guy off with a chem wipe carefully. And you don't want any bubbles on the inside here. Right? So bubbles are going to give you scattering, plus they're going to mean that you do not have your analyte in there. Right? And so just to do your baseline correction, you just take your corrected absorbance, adjust your measured absorbance, minus the baseline or your blank absorbance. Okay? So don't touch the clear faces. Usually there's going to be one frosty side and one clear side. If in doubt, make sure that you just handle them from the very tippy top. You want to keep the containers covered to exclude dust, which scatters light. Usually in a college lab, we're not going to be leaving our samples around long enough for them to pick up that much dust to where it's a problem. But your good protocol and your good lab technique says you want to cover those. We're not going to cover ours most of the time. Right? Okay. Positioning our cuvettes. precision of replicate absorbance measurements with a diode array spectrometer with a 315 nanometer dichromate solution, right? We got our filled circles where the sample was not removed. And then the open circles and squares is when you take it out and you put it back in. So your positioning error can have a impact in your RSD and your relative standard deviation in your error. Relative standard deviation in your measurement. So you've got the, you've got to be careful that if you can, leave your thing in the same way the whole time. But if you can't, just, be aware that you may have some positioning error. The variability in the position of the cuvette more than doubles the relative standard deviation. Your standard deviation is like a percent, so you're going from like a 1% up to a 10%. The modern spectrometers, modern cell holders are pretty darn reliable. Like the instrument we use that carry UV-Vis, the positioning error in that instrument is really, really small. It holds that in there in a very tight configuration. It's got like a little spring that helps keep it pushed up to a particular corner, and so your positioning error is smaller. In some instruments, like I don't know if you guys did any UV-Vis measurements in 120 lab or 130 lab, where you've got something that's really just a machined square and you plunk your cuvette into it. Sometimes we had those for MeasureNet, and some of those did not exactly fit the cuvettes. They were machined to be for a particular size, and then these cuvettes are a little bit larger, and so you have to get them out with pliers, and it was a pain. But positioning error matters is what we wanted to get to. Last, we've got our light detector. That's going to measure the irradiance at on our sample. Our spectra, our sources. So let's take a look at our sources. They can come in one of two ways. You can have a broadband or a continuum source, like in A. So this would be like a light bulb, like a xenon lamp, or a regular old light bulb that's going to give you all different wavelengths of light, and then you kind of pick the ones you want to use. Alternatively, you could have something like a line source. So something that would be either an atomic emission, so we've got a hydrogen light bulb back there, or a deuterium light bulb that's going to give us some very intense ultraviolet lines. And that line source is only going to have a couple of narrow bands to it. Probably the ideal line source is the laser. So this is how the first laser worked. You had a totally reflecting mirror. You had a ruby rod in the middle. And then you have these flash lamps around the side that would provide the initial energy for that laser. So they would basically pump that laser full of a bunch of energy. Light would start going cascading back and forth, kind of like if you had one of those old timey, like if you had a bucket, right? You had a bucket and you start splashing this bucket, splashing the bucket, splashing the bucket, and you start building up that energy. Eventually, it's all going to spill over the top. Because this cavity is a particular wavelength, light will constructively and destructively interfere in it. Just like if you've got a flute, right? You've got a certain length of your cavity, and that's going to reinforce one sound wavelength. The same thing happens with your laser, except it's an optical wavelength, and only one wavelength of light gets through. And so if you look at old-timey lasers, they've got like little fins on them. That's coming in and being that flash lamp for you. All right, so your continuum sources, again, it depends on what range of light you need to look at. So xenon arc lamp, that's going to give you stuff between 250 and 600. That'd be something that's really good for fluorescence. A lot of those fluorescence experiments need you to throw in some UV light for that thing to fluoresce, right? So if you have ever been out to the club and you're underneath the black light, right? That black light is actually ultraviolet light, and so your neon stuff is going to be fluorescent. You're exciting that with ultraviolet radiation. H2 and D2 lamps, they're going to give you UV light for molecular absorption. So the UV-Vis that we did had a deuterium lamp in it. Tungsten halogen lamp, right? Just like the ones you buy at Walmart, right? The standard tungsten tertiary lamp. All right, that's going to give you wavelengths from 240 all the way down to the infrared. So you're going from UV to IR. It's a great source because it's giving you such a broad range of wavelengths to choose from, and it's really cheap. Right? A regular tungsten lamp is not going to burn as hot. So the reason why the tungsten halogen lamp gets you a little bit further out into the UV is that they fill that chamber with a halogen. And so that halogen is going to help protect that filament. It's really just acting like, here is a tungsten wire. It's going to act like a black body radiator. If we fill that with air, right, it's going to burn out a little faster than if we fill it up with a halogen. Right? It'll be visible to near IR. A Nernst glower, a nichrome wire, and a glow bar are all really the same trick. It's I'm going to get a piece of metal hot, and it's going to give off some photons like a black body radiator. And your Nernst glower or your nichrome, your Nernst glower is going to go all the way up to 400, but you're usually going to use those in the IR. So let's talk about the wavelength analyzer. So in many ways, this is the heart of your instrument because it is what is going to separate the components of light so you can get a spectrum, right? Your spectrum is going to be some sort of intensity or absorbance or something on Y, and then it's going to be wavelength or nanometers or energy on X, all right? And so this is the, how do we get that X-axis, right? So you need that X-axis. Your detector gives you Y, and your wavelength analyzer gives you X. So there are two ways to do this, right? So if most often you're going to have some sort of monochromator, meaning one color, right? We're going to look at one color at a time. And that's because most of our detectors are colorblind. They're just going to measure, hey, I saw a photon. And they're not going to care what wavelength that photon is. So our monochromator, there's a couple of ways to make a monochromator. Probably the easiest, most basic one is just to use a filter, right? So if you want to look at blue light, you get yourself a piece of blue glass and you stick it in your beam path and it blocks out all the red light. So that's pretty broad band, right? You're not going to be very specific about it. You're like, okay, I'm going to keep some blue and throw away some red, but it's really, really, really cheap. So if you want to make something that is a low cost instrument, well, maybe that's going to be fine. An expensive way to do that is something called an interference filter. So a high-end instrument, or if you were looking at something like if you've ever seen those biology images where they've got, like, here's the inside of a cell and they're doing a fluorescence image on the inside of the cell, where they're doing laser-induced fluorescence, that's going to use an interference filter. And those interference filters are made up of layers and layers of material that when light of all frequencies hits it, they're going to undergo constructive and destructive interference. Only one or a very narrow range of wavelengths gets through. And the cool thing about these interference filters is we are now able to make them in pretty much arbitrary ranges. So if you want something that is a filter that will let through 530, 680, and anything below 700 nanometers, you can do that. Or if you want to let something that only lets through light at 420 nanometers, plus or minus 10 nanometers, you can do that. Right? The problem is that these things are very, very expensive. Right? So an absorbance filter that's like, it's blue, or it's red, or it's yellow, right? You can buy a piece of glass at Hobby Lobby, plunk that sucker in, right? That's going to cost you pennies. An interference filter is going to run you at least $100, and it could go up into a couple hundred. So 300 is not atypical for some filters that I've bought, but they could get into thousands of dollars. And so they are expensive. You can have a slit-based monochromator. This is by far the most common, right? So the slit-based one. You can have a prism that spreads your wavelengths out. So they're both going to do the same thing. You're going to spread all your wavelengths out and make a rainbow, and then you're going to put a slit in, and you're going to block out all the colors except for one wavelength. So you can spread your wavelengths out with a prism. Prisms are heavy, and they're fragile, but they're cheap. Honestly, you are not going to see a prism-based instrument unless I dig one up out of the archives of old stuff that's sitting around Bueller Hall. Nobody is going to make anything with a prism. I happen to use I don't even think the IR that I used, which was literally ancient from the 1950s, had a prism. One of the cool things about those IR ones is like in the olden days, the prism was made out of a big old chunk of salt. So like everything in those things was super fragile when it comes to humidity. And oops, I spilled my soda on it. What you're going to see now almost exclusively is a grating. A good grating can be expensive, but a cheap grating is like those little sunglasses in plastic that they had outside the little demo case on our way to the ICP, right? So you can get a cheap grating that is super duper cheap and probably cheaper than a prism. Whether or not that's going to be good enough for you to use in an instrument is another matter. There's a couple of different ways you can make a grating. There's the shell gratings and ruled gratings and holographic gratings. And we could do a whole thing for an hour on just gratings, but we shan't. So this is how wavelength selection by dispersion is going to work. So both your prism and your grating are going to be dispersion elements. Dispersion means spread the light into its component frequencies, and they're all going to basically work in the same way. So you should be able to draw and explain this. Right? This would be a good section 2 type of question. Can you draw and explain what's happening here? All right, so let's take a look at this first one. So in this first one, our reflection grating, we've got a reflection grating. Light of all frequencies is going to come in through this entrance slit. Right? Once it comes through that slit, it's going to start to spread itself out, and then you're going to focus it with a mirror and get all of your light nice and parallel. That parallel light is going to hit your reflection grating, and it's going to rainbowize it. So you're going to get some, you'll get some red, and then you might get some blue. And so you'll hit this other concave mirror, which is then going to focus the light down towards this entrance slit. Now, your focal plane, right, that's where all of your light is going to be at its narrowest. Everything's going to be focused down. And you're going to put another slit. So here, this wavelength number 2 is going to be able to go through the slit and on towards the sample, whereas wavelength number 1 here in the dashed line is going to hit this wall of the slit, and it will not make it through. So you've got 2 options. Right? You can, if I want to get wavelength number 1 through instead of wavelength number 2, I can move the slit, which is kind of a weird way to do it. Nobody would ever do it that way, because kind of moving that slit is a tricky thing to do. So what they do instead is you take this grating and you rotate it. And there's a little stepper motor that's going to turn it a certain amount, and you can correlate by degrees of rotation which wavelength of light gets through. Okay, so you're going to turn that grating, and you're going to make that rainbow move lefty-righty, and only one wavelength of light gets through at a time. Okay? Something similar happens with a prism. You've got an entrance slit over here. You've got a collimating lens that then gets your light nice and parallel. It goes through a prism. You end up with rainbows happening where either one wavelength gets refocused on the focal plane over here to hit the wall, and the other one is able to make it through the slit. Again, you're going to rotate that prism around. And if we had an old Spec 20, I would show you how that works, where you're literally, you've got a knob, and that knob moves a little arm, and that little arm basically rotates one of these things. So this is how your wavelength selection works by dispersion. There are pros and cons to a grating versus a prism. One of them is the linearity of dispersion. So if you look at a prism, right, and what's coming out of the prism, you've got 200 nanometer light over here, then 250, then 300, then 350, then 400, then 500, then 600, then 800. And all of those red wavelengths of light get bunched up at the end. That has to do with how a prism works. Right? So the red light is affected or bent less than the blue light. That's part of why the sky is blue. So if you have not seen it, I need to add minute physics. Why the sky is blue. So that's why the sky is blue. So the fact that this over here is more spread out is because blue light is more easily diffracted than red light, because as we transit from one medium to another, it's going to undergo a greater, it's going to be a wavelength dependent shift in the angle at which it comes out. For a grating, that's wavelength dispersion is nice and even. 200, 300, 400, 500, 600, 700, 800. And so you're better able to resolve things down here at this lower energy end of the spectrum than you are with the prism. And so as you can see, it's a little bit easier to make something with the grating because these are evenly spaced. Right, if I wanted to go between 800 and 801, right, that's a teeny tiny change, whereas between 200 and 201, that might be a bigger change. So it'd have to have some sort of nonlinear control in rotating a prism versus rotating a grating. Like I said, that is the reason why that works is because that's how light transits media from one thing to another. So prisms work because the speed of light is not constant. So whenever you see someone say C is constant, that's because it is in a vacuum. As you go from one media of one refractive index to another, and Snell's law says you're going to bend that light. Well, that refractive index is wavelength dependent. And so blue light is more susceptible to bending than red light is. Blue light's more susceptible to scattering than red light is. And again, vast oversimplification. But if you imagine, here is my media, and it's got atoms in it with electrons. My blue light, which is oscillating faster, is going to have a higher chance of running into a stray electron on one of my pieces of matter than my red light, which is taking its time. So red light, long wavelength light, is always less susceptible to bending because it is less affected by the refractive index changes. Our diffraction grating, on the other hand, is a reflective or transmissive optical component of a series of closely ruled lines that separate a beam of white light into multiple beams called orders. So if you look at this, here is a transmission grating. So light is, it's a transmission light grating if the light goes through it. It's a reflection grating if the light bounces off of it. So here's our incident light. And we've got order 1, which is really, really bright. Okay, I also need to add the rainbow conspiracy lady. So the rainbow conspiracy lady is awesome. So we've got this, so you end up with a rainbow. So if you look at, this is our first order. This is coming off in order number 1. And then you've got a order n-1 going this way. Then you've got a second order diffraction coming off of this, in which the colors are going to be reversed. So your second order diffraction is going to have opposite colors. So that's why if you look at a rainbow and you look at a double rainbow, the colors are backwards on the inside. And then there's actually like a third order that would come off too, but you can't see it because so sometimes you can actually see a triple rainbow, man. What does that mean? It's a triple rainbow. So you can see a second order diffraction pretty easily. A third order diffraction, kind of hard to see. There is even fourth and higher orders. It's just that they exponentially gets harder and harder to see and less intense. So here is our second order. The most orders are further separated into wavelengths or colors. The naturally transmitted beam is 0, n equals 0, and it is not separating the colors. So all the higher orders and bigger or less than 0 exhibit color separation because diffraction causes longer wavelengths to bend more strongly than shorter wavelengths. So how is this going to work? So the transmission grating with an incident light normal to the groove. So here's our incident light that's coming in. So we've got a light coming in. Each groove is going to act as an individual radiation source. So you guys might have remembered that whole particle wave duality experiment where you've got the two little holes and then the light's going to come and it's going to go through those holes and it's going to interfere with itself. that's exactly what's happening. Each of those holes is going to act like a separate source. So when light rays are diffracted at an angle, the lower rays travel an increased path, d sine theta, and at angles where an integer number of wavelengths is equal to an increased path length, the adjacent light rays are said to be in phase and reinforce each other. If they're out of phase or completely out of phase, they're going to unreinforce each other. And so we get this equation here where we get n lambda is equal to d sine theta. If your waves are next to each other, they can be in phase. That'll be constructive interference. If they're completely out of phase, it'll be completely destructive interference. And if they're kind of in phase and out of phase, you get something that's complicated and in the middle. Different wavelengths of diffracted light are going to experience constructive interferences at different angles. Right? So as your incident light comes in, right, at one angle, blue light will be constructive, and at another angle, green light will be constructive. The reflective diffraction grating can be rotated to change which wavelength is sent through the exit slit in the experiment. The reflective diffraction grating is ruled with a series of closely spaced parallel grooves. It's coated with a layer of aluminum that gives it the reflectiveness, and then you get a thin layer of silica on top. And basically, you're doing this whole constructive thing, except you're doing it as a reflection rather than this guy in the transmission grating where each one was acting as a point source. It's the same trick. It's just that one has the light bouncy offy and the other has the light coming through. You can get laser diffraction off of a compact disc. So if you see a compact disc, you've actually got two diffraction gratings going. One is the series of tracks that go out concentrically, and then you've got another grating that is formed by the actual information on this track. And so you usually get a very strong diffraction from the radial pattern, but you'll also see one happening from the actual data itself. And so you get a rainbow, you can bounce a laser off, and you can see here's my first order diffraction and my second order diffraction. Sorry, this would be my pure reflection. And so this would be my 1, and this is my 2. And then here, if you shine in both red and green, you can see that the green is bending more than the red is bending. The slit that you're passing things through is also going to have an effect on what your spectrum looks like. The wider the slit, the lower the band resolution. The wider the slit, the more photons get through, so it might be easier to make your measurement, but you're doing that at a cost of, excuse me, at a cost of precision and how narrow that band is. So if you set your slit really wide, you might let through 5 nanometers worth of light at a time, which means your resolution is, you can't really say, well, I got 101.2 nanometers as my peak, right? Because you're looking at a marker. So imagine trying to draw something with a really fat marker, right? It's not going to work too well in terms of resolution, but you might be able to see something far away. So you might get more stuff coming through, so your throughput is higher. So you've got a slit width that is going to show up as a bandwidth in your spectrum. Okay, excuse me. So filters, they were another way to do our wavelength selection. An interference filter, like I said, is going to be really narrow. An absorption filter is going to give you a range of wavelengths. There are other exotic filters out there, such as a liquid tunable optical filter or a Leo filter. Those are basically going to act as fancy interference filters, but they're going to set up that interference pattern as an optical trap, basically. So you're going to set it up as different areas of different densities by setting up an acoustical wave inside a chunk of medium, or they're going to set it up as a series of zones using liquid crystal. That's the liquid crystal. Oh my gosh. Liquid crystal tunable optical filter. A Leo filter works with like these polarizing plates that you throw in there, but really I'm going to filter stuff out. Detectors, they're going to be the eyes of our spectroscopic system. We need some way of translating the incoming photons into a measurable signal. This process of measuring one phenomenon in place of another is called transduction. We can transduce photons into a number of different measurements based on the physical phenomena, such as the photoelectric effect, by far the most common, absorbance increasing temperature, so you can use a bolometer in there, so you can actually measure temperature. Some of the early experiments, like how did they discover UV and infrared light? Right. Well, you know, somebody was smart enough to go, okay, I want to do the series of experiments where I measure how much temperature change I get with light, because sunlight's hot, right? So you stick a prism in there. Now I've got red, yellow, blue, green. Well, which one's the hottest? Is it red? Stick a thermometer in there. Is it blue? No, stick a thermometer in there. And then it's like, well, I'll just do a control experiment and do something below red. Oh crap! Like I'm getting energy out there. So infrared below red. And I'm like, well, okay, well, what happens if I go and stick it up above violet? Right? Oh, well, they're still getting some photons out here that I just can't see them. They're ultraviolet or above violet. You can do it in a charge storing device, so a charge coupled device. Lots of things use CCD. Your phone uses a CCD for its camera. Tripping an avalanche voltage, so you can have a diode or a reverse bias diode. So there's lots of ways we can detect photons. You could use photographic film, right? So that's going to undergo a chemical process, but it's still transducing photons into something else. Okay. So signal transducers, where you're going from photons to electrons, but you could do your eye, a photodiode, a phototube, an avalanche photodiode, a charge coupled device, photographic film, a thermometer, photomultiplier tube, a microchannel plate. That's what infrared night vision goggles use, microchannel plate, a bolometer. Lots of different ways we can get these photons into something else. Properties of our detectors. You've got something called dark current that you will often see. That's when, even when you've got no light on a detector, you may still see a signal. So if you get some negative intercepts in that lab where we did the UV vis, that may be why, right? You may end up with some dark current. You're going to have something called signal to noise ratio, right? The ratio of the signal intensity to the fluctuation of that background because of either instrumental noise or stray light or other processes. And of course, detection limit. That's the lowest measurable signal that is certain to be a real measurement, and that's 3 sigma above the noise. Right. Our detector response. So how efficient are we at converting a photon into an electron or something else measurable is going to depend on what that detector is, right? So our eyeballs are a great example of that. Right? We are not really good at seeing stuff below 800 nanometers in the infrared, right? You can't see in the infrared, you can't see in the ultraviolet. As you get towards the edges of those things, right, you may be able to see, depending on what eyeballs you were issued, you might be able to see stuff that's a little bit shorter than 400. You might be able to see like 380 nanometer light, but it's going to look really dim, right? You won't be like, oh, that's bright, right? But you're still actually getting a lot of high energy photons in. It's like also how your ears have a lower range and like really low bass. In order for you to hear it, you actually have to crank the amplitude way up, the power way up. And so your perceived power is way less than your actual power. And that's why bass is really damaging to your ears. Same thing is going to happen with our photodetectors in a spectrometer. What they're made out of is going to give you a different instrumental response. So something like a silicon detector, which is probably one of our most common, is going to work over about 200 to 1,200. So it's not going to work too well out in the IR, right? So our relative sensitivity, they've normalized all these things. So our photomultiplier tube, right, it's going to work over the same range, and that's going to roughly be in the visible, which is great for us if we're doing UV vis. But notice how this guy here, right, kind of craps out at about 400, right? You're not going to be able to do ultraviolet with that, right? Something like this, the silicon, this with the blue enhanced silicon is going to reach further out into the ultraviolet for you. If you wanted to do infrared, you'd need to switch the material that your detector is made out of. This one's like an indium gallium arsenide. It's an InGas detector. A gallium nitride is going to work great in the ultraviolet, but it's going to be crap out in the IR and even in the UV. So you're going to have certain peaks in here. So the absolute voltage that you might measure or the absolute current that you would measure is going to depend on what this detector's wavelength response is. So which detector you pick depends on what spectral range you're looking at. So it's also going to depend on what the light intensity is. So high as in absorbance or low as in fluorescence. So a detector for fluorescence, where you're looking at very few photons coming out, is going to be totally inappropriate for something that's a UV vis experiment where you're looking at a lot of photons and you're looking at, I'm going to drop some out, right? You see the same thing if your eyes are accustomed to the dark. You're used to looking at a very low signal, right? And then you go into a room that's well lit. It's like, I can't see anything, right? And the opposite would happen if you are accustomed to working into a bright room and then you walk below decks on a ship. It's why pirates have eye patches, right? And so when you go from a high light environment to a low light environment, you can't see anything either. So you got to pick the right detector for the job, both in terms of wavelength and in terms of what your expected photon flux is. And you might want to know whether you're looking at a single wavelength or a narrow range, or whether you need a full-on broad range. You got a couple of ways you can get noise into your measurements. I'm just going to give you the categories of these. I do not expect you to know the math behind all this. So you've got some readout noise. That's just like, okay, I'm making a measurement. I've got some electronic noise that's associated with that. I've got a variability in the last place. You can have photon detector shot noise. So if you've ever turned to a empty radio station and you hear like some crackling going on, that's because you've got radiation out there in the universe that you're picking up on. It's kind of random. It's always there. So that's this kind of shot noise that's happening. You can have cell positioning uncertainty or fluctuation in the source. That's a little more instrumental. So you've got 1, 2, 3 basic sources of noise, right? These are kind of random. This one is random but constant. These ones are a little bit random and they could be constant, they may not be. All right, different detectors are going to work over different ranges. So your photo tubes and photo multiplier tubes, they're going to work from the UV down to the IR. Silicon photodiodes, they're going to work from the near UV down to the IR. And photoconductive cells are going to work pretty much in the IR. So they're still detecting photons. You can look at a thermal change. So a thermocouple, a bolometer, a pneumatic cell, or a pyrolytic cell. Not too many of these being used. Pretty much anybody doing IR now is going to use one of these photoconductive cells. I almost guarantee that if I took apart that FTIR over in the balance room, I would find one of these and not one of these. But phototubes and photomultiplier tubes, yeah, those are really common. Silicon photodiodes, not so much these days, except for 2 applications. One is if you're doing single molecule detection. So in that case, you're taking a photodiode and you're basically running it backwards, and to the point where it is just the tiniest little bit of energy is going to cause that thing to break down and conduct. And then you will see them as diode array detectors in really just chromatography. There is a very slow process of change by which people who do separations adopt new spectroscopic instrumentation. So I think the detector on our HPLC is a diode array detector, a DAD. It's a DAD, got the DAD bod. So the diode array detector is pretty much the only other place you're going to see a silicon photodiode. In places where those have been, they've been largely replaced with CCD detectors, so basically camera chips instead. Here is probably the most important photoreceptor, and that's the one in our eyeballs. So the back of your eye contains photosensitive cells called rods and cones. The light comes in and impinges on those, and it's translated into nerve impulses. So you're still taking a photon and you're converting it into an electron. And it's translated in nerve impulses, and that goes from the optic nerve to the brain. Rod cells detect dim light but can't distinguish color. And cone cells operate in bright light and give us color vision. You know, if we were a mantis shrimp, we could see a lot more because they got lots of different colors that they can perceive relative to us with millions of times more color. It's a lot. But basically what happens with all of these is you've got some sort of chromophore, and this is 11-cis retinol, and it's stuck to a rhodopsin. And as the photon comes in, boom, this guy's going to isomerize from a cis to a trans. And it's going to basically kick off a process. When it does that, where it moves the proton down to the chain, and it goes down as an electrical impulse into your brain. Probably the second most important one in terms of spectroscopy is this guy, which is our phototube. So it is literally a vacuum tube. You have a cathode in here. Inside this glass envelope, photon comes in. It's going to knock off an electron from our cathode. Right? We apply a potential between the cathode and the anode. We get an electron that gets kicked off. Well, I've got moving electrons. This is now going to give us a current that we can measure. Once we measure the current, we're like, good, I've measured my photon. The downside of just the phototube by itself is that that's not a lot. So oftentimes we will use what's called a photomultiplier tube. This is a top-down view of this guy. Right, so this is our photomultiplier tube. And we still have a cathode, a photosensitive cathode. That's this guy here. Radiation comes in, right, kicks off an electron, and then it's going to go towards this dynode. It's still an anode, but now we've got multiple anodes, and we're going to call them dynodes. And we've got a potential so that when this guy goes in and we kick off one electron, this dynode here, it picks up on that electron, and it's going to send out multiple electrons to dynode number 2. All right, so we go, in comes one photon, hits this guy. This guy's going to, like, let's say 3. So we go from here, we go from 1 to 3. And each of these guys is now going to get multiplied and sent off to dynode number 3. So we've gone from 1 to 3, and then 1 to 3, 1 to 3, 1 to 3, 2, 9. And then we go from each of these 3 goes from 9. So you go from 9 to the, I don't know, math happens, and it gets really big, really, really fast. And so you really multiply that current that you see, because now you've got not just one electron that's coming in, but a whole herd of electrons that keep going until they finally reach the end anode, and then they get drained out, and then you measure that current. All right, which is a good place for us to stop. So we will stop here, and we will pick it up again on Tuesday. All right, do you guys have any questions?